Okay. Meet one person as a candidate. Um, um, okay, let's start. Um, any questions? It's just one person attendance here. Any questions that you have, you can ask. I can cover that first. Any doubts, anything? Uh, if not, then I will go ahead with whatever is to cover for this week. But firstly, any questions I would like to ask? I'd like to address. Okay. Fine. Okay, let's continue. This week we'll discuss on the topic of diversity schemes and various kinds of diversity and how do we quantify diversity. And so regarding that, there is different, there can be many questions, and so we'll try to solve problems that are similar to the assignment. No. Okay, I'll wait till you join that. Okay, yeah, with that. So, fine. Let's start with the first. Any doubts? If you have, then you can go ahead. Otherwise, I will just start and solve questions. And so, um, so there is one question that that is there. So you are given. Let's say there is a system with uh, three channels, and SNRs are gamma 1, gamma 2, gamma 3, right? Three different SNRs. Okay. So this is the channel SNR, and let's make this more general also. Let's say there are capital N number of channels, and SNRs are let's say something like gamma 1, gamma 2, gamma n, right? And you are told that you have to allocate, you have a power budget. So let's say there is a power budget P, and this power is divided into all of these transmissions, right? So you'll be allocating some power to the first channel, some power to the second channel, and some power to the final channel for transmission. So this is power budget at the transmitter. Right. So the question is, now I have to so I have to find, so, so I'm given the information that, uh, let's say gamma 1. So this is, let's say, provided in some kind of ascending order. Right? So gamma 1 is less than gamma 2, less than gamma n. So given this information, my question is like, what is the order of PIs to maximize capacity? Maximize capacity. So this is the question. Um, how do you solve this kind of a problem? Now, um, so to understand this, so this is actually something known as, it comes in later in theory. So it's called water filling method. There is a big, there is a tiny proof also, but where you can actually calculate these values of PI. But I'm not asking the actual calculation, I'm just asking what is the order. Um, so, so in water filling method, let's forget about that, but this is like for your reference and it will come later. But this question or similar question is there in assignment, so I'm just trying to discuss. So for ith channel, uh, the capacity of the ith channel is some bandwidth times log of 1 plus pi times gamma I, right? So this is from Shannon's law, that C equal to B times log of 1 plus SNR, right? So this is for the capacity for a Gaussian channel, or for any channel. For capacity for any digital communication channel is log of 1 plus SNR times the bandwidth. So SNR, we know the SNR of the channel, and so then the signal power gets multiplied to it, right? Because your signal is something like y equal to hx plus n, and so your SNR becomes this thing, right? Signal, so expectation of mod h squared times expectation of mod x squared divided by expectation of mod n squared. Right? Because your signal power, your the signal power and the channel power are independent of each other. And so that is what comes out here. So this is your gamma I, this is your Ti. Your gamma is actually this, this is gamma I, right? This expectation of mod of h square by mod of n square. So this is the SNR of the channel. And then this is PL. So for each channel, you have this formula. And so the total capacity is nothing but summing over capacity for all channels. So these are all parallel channels. You are sending information in parallel to them. So let's assume they don't interfere with each other. And so this is your total capacity, right? And so you have to maximize this quantity then. B times summation I equal to 1 to n log of 1 plus Pi gamma n, right? Now over here, you know that gamma 1 less than gamma 2. So that's the question I'm giving. Gamma n. so that you know this order. So what should be the order of P so that you maximize this? Maximize with respect to uh, your power allocation vector P, um, and maximize with respect to P1, P2, Pn, this quantity, subject to the constraint that P1 plus P2 plus Pn. So there is a power budget, because otherwise this is not a problem, right? If there is no power budget, then you can just keep on increasing Pi, and then your capacity will keep increasing. So there is no upper limit. So there is a power budget. And so the answer here really is, if you see that if I multiply um, like um, so if I have this order of gamma in, then what should be my order of Pi, right? So if I multiply, let's say I have let's just take a case of two channels. So I have gamma 1 less than gamma 2, and I also have this, I have to decide on this, like P1 plus P2 equal to P. Now I can always like have two parts, right? Like uh, let us say I decide on P1 greater than P2. If I allot P1 higher power to the weaker channel, what will happen in this case is I'll get something like we can take values and see also. Let's say this is something like 1, this is something like 2, and I pick this to be, let's say total power is P. Let's say this is equal to 1. So P1 is, let's say, 0.7, P2 is 0.3. So here, if I do this, if I do P1 less greater than P2, then so P1 gamma 1, so P1 gamma 1 is 0.7, and P2 gamma 2 is 0.6, right? And if I go the other way, if I split it, same 30-70 ratio, but I split it the other way, I give more power to the second channel, then P1 gamma 1 is equal to 0.3 times 1, so 0.3. P2 gamma 2 is equal to 0.7 times 1.4. So if you crudely see, maximizing log of some quantity means maximizing the product, right? Because if you add logarithm, that means in the argument you are maximizing the product. So 1 plus P1 gamma 1 times 1 plus P2 gamma 2 in the first case will be something like 1.7 times 1.6. And here it will be same thing, 1 plus P1 gamma 1 times 1 plus P2 gamma 2. This will be 1.3 times 2.4. And you can actually very clearly see that this second quantity will be higher. Because and that is very natural. Like if you provide more power to the stronger channel, that will boost the capacity a lot more than if you provide more power to a weaker channel. So if your goal is to maximize the sum rate or maximize the sum capacity, then you should provide more power to stronger channel. So your answer here will be, if gamma 1, if this is the order of gammas, then your order of P's will also be something like P1, P2, Pn. You should, to increase, like to increase your capacity, you should give more power to stronger channel. This is so if you just want to increase the sum rate, if you're not caring about fairness of your users and all that, if you just want to increase sum rate, you should provide higher power to the stronger channel. So I hope this is clear. So this was one kind of a question that is there. Is probably not going in strict order. This I think was similar to your last assignment question, so I just gave the idea. Okay. Let me solve some more problems. So let's say you are in another. Many questions in this assignment are very simple questions that are straight. You can just use text from the lecture notes and just answer them, simple MCQ type. So I'm not going into them, but I'm trying to solve the more conceptual problems that are there. So similarly, regarding channel capacity, there is another question that, so let's say you are provided, this is very simple straight formula. You are provided a channel with SNR equal to some value, let's say 10 dB. 10 dB. Let's make it, 10 dB. And you are asked capacity of the channel. You are asked capacity of the channel per unit bandwidth. So you are asked this. So capacity, this is like, so this is capacity per unit bandwidth. This is how questions will be phrased. And this is very simple, right? This is based on the formula that you have Shannon's law, which is C capacity is equal to bandwidth means log of 1 plus SNR. And so capacity per unit bandwidth will be C by B. And so here, so C by B is the quantity that is asked of you. It will be just log of 1 plus SNR. The only thing you need to keep in mind is here SNR is in linear scale, and in your question you will typically be given in dB scale. So SNR in linear scale you have to find out. So that's in case of 10 dB it is fine, right? So 10 dB is 10 to the power 0.1 times 10. So this comes out to be 10 again. And so you can just put in, and this will come to be log of 11 to the base 2. You have to remember that this is to the base 2, and you can calculate and tell me the value. It should be something like 3 point something. That should be the answer. And the units will be bits per second per hertz. Because bits per second is the unit, like we normally say, like so and so MB, so much Mbps is the download speed. So BPS stands for bits per second. And when I divide it by bandwidth, the unit of bandwidth is hertz. So it becomes bits per second per hertz. So this unit is important. Otherwise, this is a very simple, straight formula-based question. Okay. I hope this is clear. And so, okay. And just to be clear, let's say you are, the formula for SNR is signal power. So let's say there is no interference divided by noise variance times the bandwidth. So bandwidth becomes very important. Bandwidth becomes very important. Even in SNR. So sometimes you are provided the value of N naught, the noise variance also you are provided in per unit bandwidth value. So you have to multiply it with the bandwidth. Okay. So similar slight modification of the same question is, let's say now you are told some more details, right? You are told that uh, you have in a channel, you have Px Rx distance is equal to, let's say, 100 meter, and Px power, transmit power, is, let's say, 40 dBm, right? And you are told receiver noise equal to minus 90 dB watt, and carrier frequency FC is equal to, let's just put it at 1.9 gigahertz, right? You are told all of these values, and you are also told that uh, this is a free space path loss channel, so there is no fading. Free space path loss, which implies this is something we know, there is no fading. It's just path loss, no fading, right? So you are, what is the question? You're asked what is the, you're asked what is the normalized capacity? Normalized capacity. This is a very important. Normalized capacity. So remember, whenever we say something like this, normalized capacity, this is again capacity per unit bandwidth. So this is what is meant by normalized capacity. So we know the formula, right? I think, I hope so far you are following. So we know the formula for normalized capacity. What is the formula? We just discussed. C by B is equal to log of 1 plus SNR. And so we just need to calculate SNR from whatever information is provided here, right? Calculate SNR from this information. So we can easily do it in dB. So the receive. So this is when I'm calculating capacity. I'm and I will always calculate it based on the received SNR. So received SNR is transmit SNR will always be full, but received SNR is what is important. So received SNR is firstly transmit power. So I'm transmitting at a certain power minus the path loss. There is no fading, minus there will be receiver noise, right? Receiver noise power. So there can be more things also. There can be fading, shadowing, and all of that. So all of that figures in this received SNR expression. So you might have to also include all that in some questions. But this question is very simple. You just have to kind of compute all of this. So you already know the transmit power. It is 40 dB. Receiver noise, you know, it is minus 90 dB watt. You have to calculate the path loss. So let us calculate path loss. So we are told it's free space path loss. So this should be, then what is the value of free space path loss? I think it is 4 pi. In a second. Can somebody tell me the formula for free space path loss? In linear or dB? Anyone? So what I remember is something is 4 pi d by lambda squared, right? And so this is in linear. And lambda is the wavelength. Lambda is equal to c equal to f lambda, right? Where c is the speed of light, so lambda is equal to c by f. And so if you put it here, it will be c by the carrier frequency. So if you put it here, this will be 4 pi df. Or okay, I think this is inside the bracket. 4 pi d by lambda whole squared, and so 4 pi d f by c squared, right? And where f is the carrier frequency. And so, so we know these values, and we can calculate, right? Because we know D is 100 meters. We know carrier frequency, 1.9 gigahertz, and C is 3 into 10 to the power 8, right? So this is in linear, but in dB, let's try computing in dB. So you just have to take 10 log of this whole thing, right? So it will be 20 log of 4 pi plus 20, 20 log 10 of D plus, so 4 pi by C, this is the constant part, and 20, 20 log 10 of FC. I can just put in values and calculate, and just, and then put it over there. So this is, of course, this calculation is in dB scale, right? The receiver signal, because in dB scale you can subtract. In linear scale you will have to multiply, right? You'll have to multiply the attenuation and all. So or divide actually. So you can just calculate this in dB scale. So transmit power in dB is 40 dBm, and so let us. So we need to stick to one one unit, right? One unit. So we cannot. So this is somewhere you need to be careful that we cannot be mixing all of this. We cannot be mixing all of this. So we have perfect power in dBm. So let us convert it into dB watt because noise is in dB watt. So 40 dBm is 10 dB watt, right? We had discussed this. There is a difference of 30. And then receiver noise is provided to be. Now here, when I'm writing it, this means like absolute value, right? So receiver noise will harm the SNR. So I'll be subtracting it. So this will be 90 dB watt subtraction. And there will also be path loss, in which we also have to calculate dB watt. Can somebody calculate and tell me the value? You have everything here. Just have to put in the values. So I'll bring my calculator. This is a simple calculation. 20 log 4, 5. Okay. Plus 20 log FC, which is 1.9 gigahertz. So for me, path loss is coming to be something like 78, 78.0 dB watt. just bringing them all in the same unit. So this answer will be 10 minus 90 minus 78. Is I'm getting them minus 158 dB watt, which means in linear scale it will be how much? So in linear scale, this is something like 10 to the power minus 15.8. Right? Uh, hmm. It's yeah, it's the answer. So this can be any value essentially. So in this case, actually no, my mistake here. Here receiver noise is in minus 90 dB watt. So I made a sign error. So so I made a sign error here. So this has to be subtracted, right? Because okay, so the receiver noise in this case is low. So this is not linear value. This is a dB scale value, and it is very low. It's minus 90 dB watt. So here I actually made a sign error, and um, so then this will be actually 100 minus 78.0. This will be 22 dB watt. It's my bad. So this is like the typical receiver noise value, and it is actually quite low. So that is why this kind of value is quite normal. So firstly, this is the transmit power, and so it suffers path loss, and so quite significant path loss is there, and uh, and then uh, it also faces some receiver noise, and so uh, overall this is so whenever we are computing SNR, we are subtracting the noise, right? We are comparing the signal to noise ratio. So that here comes out to be 22 dB watt. And 22 dB watt in linear scale, the value is 10 to the power 2.2. So, so my capacity here, C by B, will be log 2, 1 plus 10 to the power 2.2. And this answer will calculate. So I'm getting to be roughly 7.32 bits per second per turn. So this is a reasonable value, something like single digit. It will depend on your question, and but yeah, this is kind of the method. Uh, so yeah, just be careful of the sign that path loss when you are calculating. Okay, and then so first you will subtract path loss, and then you will subtract receiver noise, and receiver noise will most likely be negative. So you have to be careful about that. Okay, so this is capacity calculation. Now, okay, so slightly more involved is some, you might be given a table like this. I think you might be, so you have a question where you have a table like this, right? You are told you have a fading channel. Uh, you are told fading channel is there. And so in fading channel, you have something like your instantaneous SNR uh, is um, small gamma, uh, which is some uh, capital, some alpha square capital gamma, right? where let's say you are given gamma equal to something like 30 dB, 30 dB, and alpha is where, and alpha is your fading coefficient, right? This kind of thing you've seen, coefficient. So this is your typical fading channel where this channel looks like something like output y is equal to alpha times x plus n, and here your gamma is nothing but expected value is gamma is nothing but signal power divided by noise power, which is power of x divided by power of n, and alpha is a random fading coefficient, some channel like that. So you know this. And so you are also told that the channel bandwidth B is equal to some value, right? Let's take it to be 20 megahertz. Your given channel bandwidth is 20 megahertz. Okay. And for this, for alpha, there is a table. So you have some table like this, where you're told that alpha can take all of these values, alpha I, with a certain probability. So what are the values? Let's say this something like 0.2 with probability 0.25, and let's say it's 0.8 with probability 0.5, and it is 1 with probability 0.1. It is, and sometimes there are gains also, so it is 1 point, it is, let's say, 2 with a probability of 25, point, 0.1 again, 0.5, 0.75, 0.85, 0.95, and some exceptional cases, let's say it takes value 5 with probability 0.05. Okay, some random whatever. I just made up values here. Let's not make it that extreme. Let's make this to be 2. Let's make this to be 1.5. Okay. So you're told this is the profile of the channel or the fading channel that it can take. For alpha, it can take all of these values 0.2, 0.81, 1.52 with the corresponding probabilities. So you are asked firstly, what is the average SNR, which is expected value of gamma. There are average SNR. So average SNR is nothing but expected value of gamma, right? So that is nothing but, now capital gamma is known. So you have to find essentially expected value of alpha square times capital gamma. This makes sense, I hope, right? So because gamma is alpha square times, so you have to find expected value of alpha square. Okay, so what is expected value of alpha square? Expected value of alpha square. You just have to essentially, for all I, you have to multiply alpha I squared with their corresponding probabilities, right? So this is just a very quick calculation. So this will be 0.25 times 0.2 squared plus point plus point plus 0.5 times 0.8 squared plus plus 1 times 0.1 squared plus 1.5 times 0.1 squared plus 2 times 0.05 squared. You have to calculate this value, and capital gamma is given to be 30 dB. So in linear scale, this will be 10 to the power 3 watt. Yeah. dB is unitless actually. So we can quickly calculate this. Somebody can tell me the answer that could be good. I can confirm them. But okay, 0.25 times 0.2 square plus 0.5 times plus
Sir, 1 into 0.1 square plus 1.1 into 1.5 square.
yes. I just realized this was an error. Thank you so much. This was a mistake. So yeah, I multiplied wrong in the wrong way. Sorry for that. Just a second. Just a second. All right, I closed some.
0.05 into 2 square.
Where?
Last
Oh yeah,
term.
yeah. Correct. So yeah, this you have to just calculate and tell me. And yeah. So it's the probability times the magnitude squared. So just I'm getting it to be 0.755. This is the answer that I'm getting. And so you can just plug in now over here, and so you can get the answer. It's 0.755. This into this, right? So and this is 755. In dB, you can calculate. So just don't mix up. When you are calculating in linear, calculate in linear and then convert to dB. Okay, so first calculate in linear, so it is 755, and then you convert to dB. So this will be I'm getting to be something like 28.7 dB. Yeah. So the mistake that can happen here is that you can 1 second. Let me just check. So one mistake that could have happened is if you multiply 0.755 directly with this value gamma in dB, 30 dB. So if you did 0.755 into 30, your answer would be wrong. Why? Because this formula is itself not in dB scale. This is formula in linear scale, right? So if you have to calculate in dB scale, you have to write the formula in dB scale. Then gamma dB will be, then this expectation of gamma dB will be expectation of alpha square also in dB. You have to convert this also in dB scale, and gamma you have in dB scale, which is 30. So then you have to operate completely in dB scale. So don't mix linear and dB. Just be careful, otherwise it's very easy problem. So now you are asked, so this is average SNR, and you are now asked this thing. You are now asked ergodic capacity of channel. What is ergodic capacity? Ergodic capacity is so C is equal to nothing but your bandwidth, whatever your channel bandwidth is there, times expectation of this quantity, right? Log of 1 plus gamma, right? SNR. Log of 1 plus gamma, where gamma is your SNR. So So you're taking expectation of log of 1 plus SN1. So how will you take it? And your gamma is this thing, alpha square gamma, and you have this value of alpha I. So your random variable here is the fading coefficient. So you have to take expectation over your fading coefficient. So just remember that. So this thing then you have to calculate accordingly, right? Your expectation over this thing, log of 1 plus gamma, is summation over all I. You have to take the probability of the fading coefficient times log of 1 plus alpha I squared times capital gamma. Does this make sense? Because your gamma is the instantaneous SNR is alpha squared times this capital gamma. And so you have to take expectation of this whole quantity, log of 1 plus gamma. So you will multiply it, basic probability statistics, right? That you know this formula, right? That expectation of f of x is summation over this thing, summation over probability of xi times f of xi, right? Overall I. So this is for discrete random variable. So same formula I'm applying. So here instead of x, I have gamma, and f is log of 1 plus gamma, and so I'm just multiplying it. Actually, gamma is alpha squared times capital gamma. So my random variable is alpha. And so I'm just applying this concept from probability statistics course and calculating this. So now what do I have to do? I just need to plug in value of alpha I and p alpha I over here. So I think you can do that. Capital gamma I'll use in linear scale, which is 10 to the power 3. So this will be, again, simple calculation. I'm not repeating it, but I hope you can follow, right? I'll just maybe write down the step, then you can do calculation. So 0.25 times log of to the base 2. So this can also be a source of calculation mistake. Just remember this logarithm is to the base 2. 1 plus this thing, 0.2 whole square times gamma. Gamma is in linear scale 10 to the power 3 plus this one again 0.5 times log of 1 plus 0.8 squared times gamma plus 1.1. Actually, this was also mistake. This was 0.1 times 1 square. So I think I made a mistake here. So this probably answer came out wrong. Okay, so this correct this by yourself. But yeah, just be careful. So this will be again 0.1 times log of 1 plus 1 squared times 10 to the power 3 plus this 0.1 times log of 1 plus 2 squared, or sorry, 1.5 squared times 10 to the power 3 plus 0.05, I think, like, that's the value, 0.05 times log of 1 plus 2 squared times 10 to the power. So this is just, you just have to do the calculation and get the answer. So I'm leaving this calculation to you. If you want me to do, I'll do it. Otherwise, I think this is simple. So this is how you calculate ergodic capacity. And of course, once you calculate this expectation, you have to multiply with the bandwidth. So the bandwidth value is provided in question. It is 20 megahertz. So that is 20 into 10 to the power 6. So you can just find this and do the calculation yourself. So now let's say you are asked that what is, let's say, SNR of flat fading channel, something like this. Fading channel with uh, same capacity. So you are asked that instead of all of this kind of this kind of a fluctuating fading channel, where you have multiple fading values with various kind of probability. So um, so this is like an ergodic capacity channel, right? So instead of that, let's say you calculate this from this previous part, you have calculated this value C. So you are asked what is the, if you have only single channel with single fading coefficient, something like this, one simple channel, then what will be the effective SNR? So essentially you are asked that with the same value of capacity C, if I write it as something like C equal to bandwidth times log of 1 plus gamma naught, some effective SNR. So here you know C, which is something you've calculated over here, right? Or you at least know C by B. Let's say in question you are not given bandwidth. In this question you are given bandwidth. Let's say in question you don't have bandwidth, but you can at least calculate C by B, right? From previous part, if you didn't know bandwidth, you could calculate this part. Expectation of log of 1 plus gamma, you could calculate. And so that is all you need. So essentially, you have already calculated left-hand side from previous part. And now you have to calculate this thing. So that is what has been asked. SNR of a single simple flat fading channel. So what will be the effective SNR? So from here, you can essentially calculate gamma naught. You just have to write it in formula. It will be 2 to the power C by B minus 1. So you can just plug in and get your answer. Okay. And you can also report in linear or dB scale. Okay. So this is one kind of question. And you are also asked maybe some variation that for same channel, you are given if there is let's say there is some 5% chance of outage, what is the ergodic capacity? You're asked this question. If there is 5% chance of outage, what is the ergodic capacity for the same channel? Now, what happens? What do you mean by outage? By outage, you mean that capacity is zero, essentially, right? Outage is zero capacity. You are not being able to transmit any information on the channel because of whatever reasons, because of maybe some extreme turbulence or disturbance, or it's very bad. So, or some kind of line of sight link is failing, or in case of wired networks, some disruption in cable or something. And uh, so this kind of question, how will you tackle? You have already calculated C in the previous part, right? Here you were not told anything about outage. So here the assumption was that if there is no outage, this will be the capacity, right? You have kind of calculated that. So when there is outage, it is zero capacity. So your average capacity will be probability of outage times 0 plus 1 minus probability of outage times the capacity that I have calculated earlier. Because when there is outage, I have no capacity in the channel. I cannot transmit any information. It is useless. But when there is no outage, which is the rest of the probability, this is probability of no outage, then I can transmit at the capacity which I've calculated earlier. So I just need to multiply this 1 minus P out. And what is P out here? Probability of outage, 5%. So that is 0.05, right? Times this value of C. And C I already know, I've calculated from the previous one. Okay. So you just have to again plug in value and get your answer. So I hope this part was clear. Now, the slightly more conceptual question is, what is the upper bound?
Excuse me, sir.
Yeah.
Sir, what is that C raised to the power? 1 minus 0.05 into C raised to the power?
It's not C raised to the power, it's just because it's a C. So it's a C. So you understood there is no power. Sorry, there is no power. I'm just saying that this is C that you have already, you know the value of C.
Okay.
That is what I'm just okay. I'll just mark it as a tick here. It is not a power.
Okay, sir.
You just know the value of C, which you have already calculated over here, right? This calculation that was there, expectation of log of 1 plus gamma. So from this calculation, you have already calculated C. And so all you need to do is you need to just put it here and then you will get your answer.
Okay, sir.
Okay. So now you are asked what is the upper bound on ergodic capacity. So this actually requires a use. I think in previous class somebody was asking. So I might have made a fine error in explaining at that time. So this requires you to use Jensen's inequality. So what is Jensen's inequality? That so this is essentially for there are two kinds of inequalities for convex and concave functions, but let us stick at least in this case. I have this function, right? Log of 1 plus SNR or 1 plus gamma. So can somebody tell me what kind of function log is? Is it concave or convex? Do we know? This is how log looks like, right? It's some function like this. This is how log of x looks like with respect to x. So is it convex or concave? This is a concave function, right? How to find BER of Nakagami M? I'll come to that. Come to that in a minute. Okay, so for now, okay, this is a concave function, right? Because by definition, pictorially, if you see, if I draw a line between any 2 points on this curve, so this is at point x1, x2, this line is coming below the function itself. So that is why it contains the line. So it is called concave function. So it's this kind of pictorial understanding. And so you can actually prove that for this function, let's say for x1, x2, if I take expectation of this function, then this will be, so I have two quantities here. First quantity is expectation of this function over this random variable x. And then I have another quantity, which is I first take expectation over x. I take expectation over x. And then I calculate the value of that function. And what Jensen's inequality says that for concave function, this is a less or equal to relation. Pictorially, if you see that if I take this for log function, if I take expectation of the function itself, let's say just between these 2 points, x1, x2, I'm taking expectation, it will come somewhere here. Whereas if I take, expectation of the function will be, I'm taking essentially expectation over the y values. So this is y1, y2. So I'm taking expectation of the function. So it will come to be somewhere, if you draw this tangent chord, it will come somewhere here. While if I take expectation of x, which is this middle point, x1 plus x2 by 2, you can see that now if I take f of expectation of x, it comes above the y value. So that is why, like, this is pictorial. I'm not getting into the proof, but expectation of f of x, where x is a random variable, is less than f of expectation of x. So this is the inequality that we'll be using. So this is c equal to b times. So for upper bound, what will we do? So ergodic capacity is c equal to b times expectation of log of 1 plus gamma, and so if you take expectation, if you use this inequality, so then this will be less or equal to b times log of 1 plus expected value of gamma, right? Because your random variable here is this gamma, which is actually alpha squared times capital gamma, and so actual random variables is alpha squared. So you can just use the Jensen's inequality and write this. So this is the upper bound. So this becomes upper bound. And expectation of gamma, Expectation of gamma, because you have calculated it in first part, right? Average SNR, you have calculated expectation of gamma is expectation over alpha squared times capital gamma. So this is, you can complete the calculation over here also. And so you can just put in this value of expected. This is actually wrong. You have to complete this. So expected value of alpha square times capital gamma is expected value of gamma you have computed, and if you just put it over here, then you will get your answer for upper bound of capacity. Okay. Okay. Now here is BER for Nakagami filling. Come to the BER problems now. So actually these are very standard formulae and derivation is there in the lecture. So I will not spend too much time on derivation, but so BER depends on various things. It depends on the kind of modulation you are using. It depends on your fading, the kind of fading that is there in the channel. And it also depends on number of antennas, etc. Number of antennas and combining schemes used. It depends on all of these. Right? So we just to take into account of all of this. So let's solve actually one problem, and then I think your question will be resolved. And let's start with simpler relay fading first, and then we'll go to Nakagami. So you have a receiver. So you need all of this information essentially. You are told that RX has two antennas, and it's using maximal ratio combining, and it is a relay faded channel. Right? Okay. You have two antennas, So the average receive SNR at both antennas is not the same. So at one antenna, gamma 1, received SNR is, let's say, 10 dB. And your gamma 2 in second antenna received SNR is 5 dB. Let's say, right? So this is kind of received. It's actually, I shouldn't write it as, I can write it as average. So average received SNR in antenna 1 is 10 dB, average received SNR in antenna 2 is 5 dB. So you are asked that now what does MRC do? In maximal ratio, MRC stands for, as we know, maximal ratio combining. So the derivation is there in the lecture notes, but effectively what happens is the SNR for maximal ratio combining, effective SNR, becomes the sum total of both the antenna SNR. So that is what maximal ratio combining does. It is able to combine the effect of, so this I should write it as gamma MRC. It is able to combine the SNRs or combine the effect of both the antennas. Right. And so if I take average, I will take average on right hand side also. And so my average comes out to be how much? Now see, again, we need to be careful. These values are in dB. And I cannot just, and this formula is not in dB. This formula is in linear scale. So I have to be careful. So I cannot just add 10 plus 5 and make it 15 dB. That will give me the wrong answer. So I'll have to be careful. So this will be 10 to the power 0.1 times 10 plus 10 to the power 0.1 times 5 in linear scale. So can somebody give me the answer? Let's see. It's coming to be 13.16. So I'll just convert it into dB. Coming to be roughly, this is in linear scale, I'm converting it into dB, so it is coming to be 11.2 dB. So that's the value I'm getting. Okay. So this is for MRC, right? Now, this is how you determine average SNR. And let's say instead of relay fading, now you are changing from relay. So this is before calculating BER and all. Let us clarify this. So instead of relay, you now have everything else is the same. You now have Nakagami M fading with M equal to 2. Now you are asked to calculate gamma MRC, average SNR with MRC combined. So the question is, will anything change? Actually, nothing will change because you're told that everything else remains the same, right? If average SNR remains the same, then from formula you can see that nothing changes. You just need to still do the same calculation. So the answer is actually it essentially remains the same. The average SNR remains the same. It won't change. But what will change is for the same average received SNR, the BER will change. So this will actually remain the same. Now, when will Okay, let's first complete the fading. So now you are asked with Rayleigh fading, what is the BER? What is the BER, right? So actually this is also derived and you are told that we are using differential VPSK, DVPSK modulation. So this derivation is there in the lecture notes. So probability of error in differential VPSK with fading channel is half times this characteristic function psi of this effective SNR gamma MRC S at the value s equal to -1, right? So I'm not getting into derivation right now, but so what is this characteristic function? Characteristic function of in general any. So this is a general formula for any random variable gamma. The characteristic function is defined as this thing, right? Essentially, Laplace, it's kind of the average of the Laplacian. And so the formula is something like this: 1 by 1 minus gamma s, right? So, so this is the characteristic function, and so this is actually it comes from this. But here you take expectation over gamma, and so gamma PDF is of a form. So gamma is exponential, right? So what is the PDF of your gamma? The gamma is a random variable with this PDF, right? Exponential PDF. So if you actually put this and take this expectation, you will get this value. Now, so what is gamma for maximal ratio combining? It will be combining the SNR of the two antenna, right? So it will be gamma 1 plus gamma 2. And so when you take the combined characteristic function of gamma MRC, then this will be expectation of e to the power minus f times gamma 1 plus gamma 2. So this will essentially become product of each of the individual characteristic function. So all of this is, so this will essentially become 1 by 1 minus gamma 1 s and or yeah, gamma 1 s 1 by 1 minus gamma 2 s. Where so I use the notation earlier, so I use this notation gamma 1 bar, but you can also write it as capital gamma, and gamma 2 is gamma 2 bar. So essentially these Laplacian functions, essentially these characteristic functions get multiplied, and so this figures in this calculation for MRC. You will have to multiply these two. So again, probability of error for differential BPSK modulation and for Rayleigh fading, half of this thing, 1 by 1 minus gamma 1 s, 1 by 1 minus gamma 2 s, and everything at s equal to minus 1, right? So this will be half of 1 by 1 plus gamma 1 times 1 by 1 plus capital gamma 2. And capital gamma 1, capital gamma 2, we know it is, if I change notation here, this will be capital gamma 1, this will be capital gamma 2. This is the average SNR that we are receiving. So you can also write this as this thing. So average SNR 10 dB, 5 dB, you can just put it here. Again, convert dB into linear. 1 by 1 plus 10 to the power 1 times 10 dB is 0.1 into 10. So that is another. And 1 by 1 plus 10 to the power 0.5. So this is 5 dB. And you can calculate and get the answer for Rayleigh fading tools. So now Nakagami fading, what changes is, now let's say you are told that so both antenna have Rayleigh fading here. Now here you are told that antenna 1, so the channel to antenna 1, antenna 1 channel has Nakagami sorry, I'm writing the wrong Nakagami and fading. And antenna 2 has Rayleigh fading, right? Rayleigh fading. Now, how do you calculate the same question you asked, that differential BPSK, and so now how do you calculate this thing? Probability of error for differential BPSK with fading. Now again, this is the basic formula again stays the same. So this is half times the characteristic function of gamma MRC at s equal to -1. So this is how you calculate. The verification of this formula is there in the lecture. So now gamma MRC is so as I showed here, that gamma MRC is gamma 1 plus gamma 2, and hence it splits into this product, right? So this part remains the same. So let's say, so this logic still stays the same. Gamma MRC is equal to expectation of e to the power minus s times first antenna plus second antenna. And so it splits into two products, right? There's gamma 1 times expectation of e to the power minus s gamma 2. Now, we know that this expectation is over the fading coefficient, right? Because gamma 1 is some alpha square times capital gamma 1, and gamma 2 is some other, some beta square times some other fading coefficient. So this is all an expectation over the fading coefficient. So if the nature of the fading coefficient, if the distribution of fading coefficient changes from Rayleigh to Nakagami n, so then this expectation will also change, right? So now for second antenna, we already know that it is still Rayleigh. So for second antenna, we can still write the same formula, which is 1 by 1 minus gamma times s. So gamma 2 times s, let's say. So this still says the same. This is at, so if I have to evaluate this at s equal to -1, so this whole thing, just write it neatly. 1 second. gamma 2. This whole thing is at s equal to -1. So I'll have to take, so the second part is still the same for this Rayleigh. This is the formula at s equal to -1. For the first part, for Nakagami n, so for any general value of n, this formula is, this is also derived in the lecture, and don't think there is time for me to go over the derivation. So then this is the formula actually. So for Nakagami m, if you use the fading formula, so if you remember, this is, so I told you this formula for SNR in Rayleigh channel. So this holds for Rayleigh. So this is the Rayleigh fading formula, right? Rayleigh fading gain formula. So this formula is exclusive to Rayleigh fading. For Nakagami m fading, you actually, so this also has to be calculated at s equal to -1. For Nakagami m, actually this, so this is there in the lecture notes also, that this fading formula is something totally different. It's something like m by omega whole to the power n. You can just, it's there in this, just give me a second. It's there in your lecture notes in one of the lectures. Yeah, it is there in lecture 34. So gamma to the power n -1 divided by, this is the gamma function, standard gamma function. So this is the PDF, and actually this is average SNR. Like, so this is, yeah. So this is your average SNR. So here this gamma is nothing but expectation of your average SNR, and this is the gamma function. So this is actually Nakagami m fading, and so essentially, if you put this here, if you put this PDF over here and calculate this expectation, calculate this characteristic function for Nakagami m, it will come out to be this value. So this is just theory, but to solve the problem, all you have to do is put s equal to -1 here, and so this, let's see, probability this, so that is your DER, or probability of error for differential BPSK for this kind of a fading, will be half times. So your first antenna is Nakagami m, so you will use the Nakagami m formula. So it is, if you put s equal to -1, it will be 1 plus gamma 1 by m whole to the power m. And for second antenna, you are given its Rayleigh, so it remains the same. So that is all. So for, so Rayleigh is nothing but Rayleigh, just remember this. Rayleigh, we had discussed this earlier, right? Rayleigh is Nakagami m, where m is equal to 1. So if you can also see from the formula that if you put m equal to 1, then it's just like Rayleigh. But now let's say we put some other value. You are told that for your channel m equal to 4, let's say. So then probability of error, differential BPSK, equal to half times 1 by 1 plus, now gamma 1 was 10 dB, so 10 to the power 1 divided by 4, whole to the power 4, and gamma 2 was 5 dB, so this will be 1 by 1 plus 10 to the power 0.5. you can do the calculation and get your error probability. Is this clear? I hope your doubt is resolved.
Yes, sir.
Okay. Okay. Fine. So now another. So fading is an important part, but another thing that affects your DER is your the kind of combining you are doing. So let's say now instead of MRC, you are now doing everything else is same. So you have relay channel skills, let's say. Or doesn't matter, the fading doesn't matter. Let's say instead of MRC, you are now doing equal gain combining or EGC instead of MRC. Now you are asked what will be the average SNR. So you are asked gamma EGC. Now this derivation is also there in the lectures. So equal gain combining is essentially, so in MRC, you like, then so in equal gain combining, your gain coefficient essentially when you are combining at the receiver is this thing, Zk star by mod Zk. So every gain coefficient has equal gain, so it's the unity gain. That way. MRC is slightly different. So in MRC, you will not be doing this. So this is equal gain combining, and so in MRC you'll just be doing. So this is some other constant times Zk star. It won't be, you won't be dividing by this, and this is MRC. Okay. So in equal gain combining, you can do the derivation. So like, so for MRC, the SNRs get added. For equal gain combining, the SNRs get kind of average in a twisted way. So if there are M antennas, you will have, so in general for M antennas, you will be adding all of the SNR for all M antennas. For equal gain combining, you will be averaging the SNR. We'll be averaging the square root of SNR and then squaring the whole thing. So this is something that can be derived, but I'm not going into the derivation. So for two antennas, this will be half times root over gamma 1 plus root over gamma 2 squared, right? So this, if I write, so this will be 0.5 times gamma 1 plus gamma 2 plus 2 root over gamma 1 times root over gamma 2. Right? This will be the value in linear scale. And so my average value, if I have to finally, for average value, I'll have to take expectation of this right hand side quantity, right? 0.5 times. Now, average value of gamma 1 is capital gamma 1. Average value of small gamma 2 is capital gamma 2. And then I have to take average values of these roots. Both are independent variables, so I'm just writing them separately. I can take product. So these two I know. This is 10 dB. Capital gamma 1 average SNR is is 10 dB and this is 5 dB. Right? So this I know. But this I don't know, but it can be proved that so if everything else stays the same, if I'm assuming it is both a Rayleigh fading, still Rayleigh fading, right? So you can just prove this that so if it is Rayleigh fading, then what is the PDF? This is the PDF. 1 by capital gamma e to the power minus. This is a PDF. Actually, no, this formula was wrong. So exponential PDF essentially. For Rayleigh fading, the gain PDF is exponential. So if you just put this value, so if you just take this exponent and do the calculation, this is one of the standard integral forms that are there. And this answer actually comes out to be something like root over pi capital gamma by 2. So you can actually just go online and search for, if you can kind of do this calculation and show that for Rayleigh fading, this is the expectation. And so if you just plug in this formula, so you will get your answer as something like capital gamma 1 plus capital gamma 2 plus 2 times root over pi gamma 1 by 2 times root over pi gamma 2 by 2. And so we know, and gamma 1 we know is 10 to the power 10 dB, so it's 10 to the power 1, and gamma 2 is 5 dB, so it's 10 to the power 0.5. And just put in the value and get your answer. So this kind of question will come that average SNR, you're not as the instantaneous value or as the average value of SNR. So then you can just put in these values and get your answer. Did I make a mistake? No, it's fine. This step I hope is clear. I have just expanded root a plus root b whole square as a plus b plus 2 root a root b. So this is, you can just calculate and get your answer. That is, I hope this is clear. One last question that is there to be solved, but before that, any other doubt? So this covers the BER concept. And there is important code that has been taught, which is Alamuti code. And there's one question regarding that, so I can cover that in more detail. Okay. Any other doubts or question? That is, okay. Fine. Let us discuss this. So, question 5 is there. A similar question, like in Alamuti's code, on Alamuti's thing, you know that diversity order is equal to 2, right? So your SNR degrades twice as slowly, or yeah, your BR is even more dependent on SNR actually. So that is there, and so you are asked there is a modified LMOT coding with but normally in LMOT code, what is there? There are two antennas at two TX antennas, right, and one receive antenna. So this is your TX, this is RX. So this is your normal LMOT coding situation, and you are sending two symbols. So first you are sending S1 and minus S2 star. Then you are sending S2 star and this one, right? Sorry, you are sending S2 and S1 star. And both are going. So this is at t equal to 0. Let's say t equal to 1. So in two consecutive time slots, first time slot you are sending this is tx1, this is tx2. And so first time slot you are sending S1 and minus S2 star. And in second time slot you are sending S2 and S1 star. Right? So S1 and minus S2 star, S2, S1 star, and eventually what you are ending up is at the end of two, so two times like two timestamps or two time units. You are taking up two time units. You are sending two symbols, right? So you are sending S1, S2, two data symbols. So that means you are sending overall you are sending one symbol per channel use. That is that is used. That in one channel use, on an average, you are using two channel uses. So you are sending the signal two times. You are kind of using the channel two times, and then you are sending two symbols, right? So so you are sending one symbol per channel use. So that is your efficiency is still good, and you also get through LMOT coding. You also get diversity gain, right? Diversity gain of 2. So now you are said that you are asked that you have a modified LMOT code. So how are you modifying? That you now have, let's say, n number of receivers, n RX antennas. So now you have two transmit antennas. Same symbol, same thing you are doing at t equal to 0, t equal to 1. You are transmitting S1 minus S2 star at t equal to 0, and you are sending S2, S1 star at t equal to 1. It's just that at RX you now have this thing, RX1 till you have n antennas now. Now you are asked what is your diversity gain for n antennas. For n antennas, what is your diversity gain? So this kind of conceptual question is there in the assignment. So this is actually very simple actually to answer. That like conceptually, even if I don't do any mathematics, you can see that I'm sending the same two symbols. I'm sending the same two symbols S1 and S2. And now there are capital N antennas. And each one antenna provides me two order diversity gain because there's two channels, essentially two different channel uses. So I'm getting two different channels, and because of these two TX antennas. So for each channel, I am being able to exploit full diversity. For each RX antenna, I have two TX antennas, so two channels. And because of this LMOT coding scheme, I'm being able to exploit full diversity. So if one receive antenna can exploit the full diversity, all of the receive antennas can also exploit the full diversity. And if eventually, if I combine all of these received signals together, I can combine the diversities also of all of the receive antennas. So the total diversity gain will be essentially 2 into 2 for one antenna. So it will be 2 into number of RX antennas. So your total diversity gain will be 2n. The total diversity gain will be 2n. So this is as far as how you will, your answer will be 2n. Derivation detail I can do. So I can do derivation for like any number, but it's, firstly, since there is limited time, any other question if you have, I would like to answer. Otherwise, I can just quickly show this derivation. So essentially what happens is at each of these antennas, right? So let's say first antenna, so R1. So receive symbol at time 0 for the first antenna will be Z11. This channel, first channel is Z11. This is Z11, first channel, and this is Z21, right? Or it depends on your notation. So if I'm using this is Z12 then, right? So for first receive antenna, first transmit antenna is Z11. That's the channel coefficient. And what signal am I sending on the first channel? In time equal to 0, I'm sending S1. So Z11 times S1 is there. And I'm also getting something from the second channel. So that is Z12 times, in first time instant, I'm sending minus S2 star. First time instant, I'm sending minus S2 star. So Z12 times minus S2 star is there. And there is some receiver noise, N1, at time t equal to 0. Now at time t equal to 1, the channel remains the same, but the symbols transmitted become different, right? So second time instant, I'm sending S2 and S1 star from each of the antennas. From first antenna, I'm sending S2, and from second antenna, I'm sending S1 star. And some noise. And so when I'm over here, I'll assume that channel is known. Over here, I'll assume that channel is known. So I can get a combined effective receive signal for antenna 1. That is, I'll do a trick here. I'll combine it in this way, that I'll do Z. So if I just write this in vector form or in matrix notation, if I combine these two into a vector, so something like R10, R11, then this will be, you can verify, this will be Z11, Z12, again, so if I stick to the same X variable, so I'm just trying to write it in this form, S1, S2 star. And you can just check this. So what is R1? R10 is Z11 times S1 plus Z12 times minus S2 star. So I'm keeping the minus sign in the matrix. And for R2, for R1 at time t equal to 1. So here, this is actually Z1, 2 times S1 star. And so if I take star of this whole thing, so R1 star 1, this will come out to be Z1 1 star times S2 plus Z1 2 star times S1 plus N2 star of 0. Right? So if you can see, then for S1 the coefficient is Z12 star, and for S2 the coefficient is Z11 star. Right? So this kind of orthogonality is there in this matrix. How? So I'll just show it in a quick step. Plus there is this noise vector, right? N vector. So N vector is nothing but adding just these two. So this is N1 of 0, and this I should write it as noise at antenna 1 at timestamp 1. So N vector is nothing but N1 0 times N1 1. So this is just same thing, same equations written in vector notation. And now if I do this matrix, so this is, let's say, S, this is, I denote as capital Z. And if I do Z Hermitian times R1, what will I get? So Z Hermitian is, if you remember, then in principal diagonal, we just switch. How do we take Hermitian? We just do this, right? Principal diagonal we switch, and non-principal and the off diagonal we switch and change signs also. We we firstly change position, and then also flip the sign. So that is how you take Hermitian. And then if I multiply with this one, 1 second. Oh, sorry, I forgot to take the transpose thing. And then there will be a transpose. So I'm just doing it very quickly. So pardon my mistakes. So so essentially you are doing Z Hermitian times Z times S, which is S1, S2 star, plus 1 Z Hermitian N. So I'm ignoring this term, this noise term for now. Let's focus on this part. So you can see if you do the multiplication, you will get something like mod Z11 square plus mod Z12 squared, right? And then the cross terms, if you see, they will go to 0. So this will come to 0, this will come to 0, and this will again give you this thing. Times S1 star, S1 and S2 star. So what this gives you is, you can totally, now this final output, which you can call R, is completely separated into these two symbols, right? So now if you let's say you call this your received vector y, then your y1 is, so this is diagonal matrix and this, so the cross terms don't matter. So your first term is just this times this. So first row times this column. So this will be S1 plus some noise term. So yeah, some noise term. So let's ignore that. And Y2 will be again S2 plus some noise term. So as you can see that we are combining the channel gains of two of two streams. So then diversity order actually in this case, as we know for MRC, it becomes 2. Diversity of, because from here we can detect S1. From Y1 we can detect S1. From Y2 we can detect S2. And so for both of them we get diversity order of 2. So so now if you have n antennas, what will happen is you can for n antennas, what can happen is you can actually stack all of these together. You can just keep on making this kind of stack. R10, R1 star of 1, like we made for one antenna. Similarly, you can so because when you process, you can just combine the output from all of the antennas. And so you can just keep on stacking up like this for all n antennas. And likewise, you will have Rn, Rn0 and Rn star of 1. So you can do the same kind of processing. And if you just repeat the same process for each of these, for the whole vector like this, if you just do the same kind of math, you will eventually end up with something like this, that your for each of these essentially for each of these y for you will eventually end up with the same kind of calculation. And then when you do again this so this each of these blocks is kind of one Z. And then when you again do Z, Hermitian Z, you will essentially get something like Y1 equal to some mod Z11 square plus mod Z12 square, which you got from one antenna. And this will keep on adding. For second RX antenna, this will become mod Z1, Z21 square plus Z22 square. And so you will just keep on adding them till mod Zn1 square plus mod Zn2 square. And so, so hence diversity order will become, for each antenna, there will be diversity order to 2. For n antennas, it will become diversity order of 2n. So diversity order equal to 2 capital U. So sorry, I'll do this. Let this be some kind of capital something of so this is a very quick patiently do the full group, but I don't think it's needed. You can just try. Like I showed for two for one antenna, I showed for n antennas, you can just try repeating the same process and stack up all of these R vectors and do the calculation, and you will ultimately come to this. So Y1 and Y2 will both have this kind of gain coefficient. So you can diversity order of 2. So any other doubts? This time is students joined late or started a bit late as well. But any other doubts? Then I will end this. not, thank you. I'll end this session.